Testing on Twitch. Okay. Testing. Let's do this one. All right. Oh, actually, I think we need a source params default, and then we also need to source params next. Okay. Now we can go back to here. We have a little robot operating in the background. It's gonna be beautiful. All right, let me set it up on the other screen as well. I have too many screens. This one. Okay. Good morning, Ed. Good morning, Minotaur. We're going to have our little robot buddy here helping us today for this stream. Let's see how YouTube is looking. Buddy, how many fingers am I holding up?
You're welcome. If my memory served popcorn, we'd make a cinema out.
I don't know if you guys can hear him or not, or it, but looks around.
Heard you loud and clear. If my circuits had ears, we'd be...
All right. I need to make him less of a joker.
We'd have a picnic and meal.
He's very chatty, loves to talk. Okay. And I think we just need one more here. Let's make sure X is working. I think X should work relatively soon. Okay, I think X is live as well, so we're going to go ahead and get started.
The poetry of incomplete thoughts. Just quite the conversation starter.
Alrighty, so welcome to another Hoopo stream. Got me, Hoopo, and then we got our little robot buddy over there. I'm actually going to probably mute him just so he doesn't keep chatting at us. But if you're interested in how I built that robot, definitely check out the stream on that. I'll just let him keep interrupting me. But definitely check out the stream where we go through that robot. But you can see here kind of on the bottom corner, that's the output. Or that's basically what's happening inside that robot's brain. The robot thinks in emojis a lot. Okay. So
choreographed chaos, but every step's a tango of tech.
Every step is a tango of tech. How's it going, Huge and Liu? Okay. Today's
Dance and memories the music.
Jesus Christ.
Even step.
All right, I'm actually going to kill him. Stop. All right. Today's video and stream is about video diffusion. So we've been going through a bunch of, or we haven't really been going through them, and that's why, right? There's kind of been this accumulated video diffusion papers, and today we're going to kind of try to blast through all of these video diffusion papers. So we're going to be looking at a bunch of different papers from a bunch of different organizations and kind of comparing them, but really kind of leading up to what I think is the best paper. I went over these this morning, and ultimately where we're headed is this paper here, which is the Stability AI's video diffusion paper, which I think is the state of the art. But we're going to start here. So we're going to start, and I kind of ordered these like a little bit chronologically, but not entirely chronologically. So the first one is called Magic Animate, and this comes out 27th November 2023, or came out, and this is from ByteDance. So ByteDance, I think, is the company that makes TikTok, right? But Chinese company that made TikTok, as far as I know. So here we have a demonstration on their github.io. GitHub.io is basically like a website that is specific to a paper. These are all based on a previous website that someone created a very long time ago for a Nerf paper, and now it's basically become a standard. These things are starting to almost become better than the papers. Honestly, they not just show you videos and GIFs, right? Which I think for something like video diffusion, being able to see the video is obviously a lot better than just looking at pictures of the video, such as this. But also, they're very good summaries of kind of the techniques and stuff like that. So we can see here some results, right? You're using a pose to drive an image. So basically, the input for this model is you start with an image, so this image here or this image here, and then you have a sequence of poses, or a sequence, you can think of like a video of poses. So this here, this has been recorded from some video, right? And then fed into a pose detection model. The output of the pose detection model is a single frame of basically this, where this is called a dense pose format. There's a lot of different pose formats, right? So you guys might be more familiar with this one here, which is kind of hard to see there, but it's kind of more like the stick figure one. This is a different paper. This one this one here. This one you see a lot more often. This is called a pose skeleton, right? And there's specific points corresponding to specific points, for example, on the hip, on the shoulders, on the elbows. And then those points are usually just either 2D in image space, so just a single point, or basically the XY coordinate of that point in image pixel space, or sometimes they're 3D, so they're a kind of a 3D point relative to the camera position or some kind of global coordinate frame. But these here, dense pose, are basically just slightly more advanced versions of that have, rather than a single point for the elbow, for example, they have kind of the surface of the top of the forearm, the surface of the bottom of the forearm, the kind of chest area, the back area. So they're a little bit more advanced, but fundamentally it's the same thing, right? It's like a sequence of poses that are used, in this case, to animate a video. So you can see here the quality, pretty good, pretty impressive, at least for video AI just a year ago. And here they're comparing against some older versions, so TPS, MRAA. I don't even know half of these older kind of things they're comparing to, but obviously theirs looking the best. But it's still not like completely perfect, right? There's still a lot of details that are wrong here. They kind of cherry pick these results to look as good as possible, and even then you can kind of see, like, for example, one thing that they kind of try to kind of cheat here with is they use animations that are very fast, like this, and whenever the animation is very fast, you can't tell that the fingers are all messed up, right? Like if you look at the actual hand, the thumb is like backwards. A lot of times there's not even any definition in the fingers, but pretty good, pretty impressive. The background being kind of completely flat like that is also pretty nice too. Although you can see there's some errors as well right here. The mirror kind of changes size halfway through that. Okay, but that is Magic Animate. So let's go ahead and read the abstract for this. This paper studied the human image animation task, so animating a human image, or an image of a human, aims to generate a video of a certain reference identity following a particular motion sequence. So the reference identity just refers to a specific person from a specific image. And then the particular motion sequence refers to this sequence of dense poses, which are basically this, right? That's the sequence of dense poses. Existing animation works typically employ the frame warping technique to animate the reference image towards the target motion. So here they're referring to kind of earlier attempts to do video from image or animating an image from a sequence of poses. They basically try to warp the existing image using that pose, and that'll work well if there's not a lot of motion or if it's a more constrained situation, but it's not going to work as well as what they do in this paper. These approaches face significant challenges, blah, blah, blah. We introduce Magic Animate, a diffusion-based framework that aims at enhancing temporal consistency. So diffusion-based here refers to the fact that they're going to be using a diffusion model to do this, specifically a video diffusion model. Or actually, yeah, I think they use a video diffusion model here. So, and here, enhancing temporal consistency. Temporal consistency means consistency in the time domain. So temporal is in the time domain, right? And if you have a sequence of frames, which is a video, you want each frame to be consistent with previous frames and consistent with kind of all frames. And consistent, for example, the background needs to be consistent, but also the kind of subject needs to be consistent. And there's different types of consistency depending on whether you're looking at the background, the subject, and so on. To achieve this, we first develop a video diffusion model to encode temporal information. So here's that video diffusion model. Second, we maintain the appearance coherence across frames. We introduce a novel appearance encoder to retain the intricate details of the reference image. Leveraging these two innovations, we further employ a simple video fusion technique to encourage smooth transitions for long video animations. Empirical results demonstrate the superiority of our method over baseline approaches. Our approach outperforms the strongest baseline, so here they're kind of claiming state-of-the-art, but they're only claiming state-of-the-art on this specific TikTok dancing data set. So this is kind of another cheat code that people use sometimes where they basically say, hey, we're state-of-the-art, but only on this weird specific benchmark that nobody else has really used. So a little bit of a cheese strategy there, but, you know, we'll let him go through. So we're going to skip right to this figure here. So this figure here is kind of like the architecture diagram, but I think that these figures kind of give you the system overview, the pipeline, whatever you want to call it, but I think they're the best kind of summary of everything that's going on here. So given a reference image and a target dense pose motion sequence. Okay, so you have your reference image, which is just going to be a single RGB image, this one here, this like kind of person smiling. Then you have a target dense pose motion sequence, so a sequence as in multiple frames that are logically ordered in time, and then they are dense pose format, right? So dense pose is the type of pose format. And the target there refers to that's the target. That's what you want the reference image to be animated like. Okay. Magic Animate employs a video diffusion model and an appearance encoder for temporal modeling and identity preserving, respectively, left panel. So here on the left panel, divided here by this dotted line here, we have an appearance encoder, this blue part here. This is a variational autoencoder. Basically, it encodes a VAE. It encodes an image into a smaller latent, which kind of represents the semantic content of that image, in this case the appearance of the person in the reference image, right? That's kind of what they want from that encoder. So you can see here that they just basically want that the representation of the reference image at the bottleneck, which is right here. Let's zoom in a little bit because these can get a little bit dense. So that's what they're calling their appearance encoder. For temporal modeling and identity preserving. So identity preserving, right? They want to preserve the identity of the person in the reference image across the entire video. To support long video animation, we devise a simple video fusion strategy that produces smooth video transition during inference. Okay. So most of these video pipelines, they're quite expensive, right? So we already know that diffusion, even just text-to-image diffusion, is actually quite expensive because the way that diffusion works, you're kind of iteratively removing noise or denoising, as it's called, and for each image that you denoise, usually there's a set of those steps required to even denoise it. So even just one image requires multiple steps of diffusion unit, right? So now if you think about having to do that for a sequence of frames inside a video, it can get pretty expensive pretty quick. So most of these video pipelines, they will generally work at a very low frame rate. So they'll work at basically maybe just a couple, maybe even just one image per second, right? If you have a 30-second clip, you have one basically frame per second, or something a little bit smaller than that. But in order to get something like this, right, this is much faster frame rate, right? This is kind of what you're more used to if you're looking at social media or even things like YouTube. This is almost like 24 FPS, 30 FPS, right? And now think about how expensive it would be for a 10-second clip if each second is 30 frames, right? Now you're talking about 300 frames. So the way that most of these pipelines are going to work is they're going to work kind of at a higher frame rate, and then they'll have a second part of the pipeline that kind of interpolates between those. And I think that's what they're called. That's what they're referring to here with this video fusion strategy that produces smooth video transitions during inference. So inference is when they're actually using this. Okay. So here, this noisy latents. What they're referring to here is that in a diffusion model, right, the diffusion model is iteratively denoising, not even in the image, it's iteratively denoising a latent image, and the latent refers to the fact that the image has been encoded into this latent space. But what you start with is noise in the latent space, so latent noisy. Noise in the latent space, which just looks like this kind of white TV noise here, right? And for every frame that you're starting with in this dense pose sequence here you see that the dense pose sequence is also going in to an encoder, and then that encoder, along with what they're calling the appearance encoder, these parts here are being used to condition the UNet. So this part here is a UNet, which is a text-to-image unit, probably from some Stable Diffusion prior, and they're feeding in these noisy latents, and then they're removing, iteratively denoising, conditioned on the appearance from the reference image and the sequence coming from these dense poses. And you can see here the temporal attention. So you're going to see this pop up in these papers time and time again, but you're going to have this concept of spatial attention, and then you're going to have temporal attention. So spatial attention refers to attention operations, and here attention refers to specifically an attention block, which is a model architecture subunit that appears in transformer models. All these things are generally transformer models. So temporal attention refers to when you're using attention in the temporal or time space. So basically attention between the different frames in the video. And then spatial attention in these papers is generally going to refer to attention within a specific frame. So within a specific frame, you might say this image token here and this part of the image is paying attention to this image token here in this part of the image, right? That would be within the spatial attention, and then temporal attention would be this part of this image token in this frame paying attention to some other image token in some later frame. Okay. I'm kind of blasting through this, so feel free to interrupt me with questions here. Okay. So all right, then you get the latent, denoised latents. Once you have those denoised latents, then you can, let's see what they're doing here. Dense pose sequence 0, dense pose sequence 1, noisy latent 0, noisy latent 1, and then the reference image, and then image video joint training, which I think is this part here in the beginning. Yeah, so whenever you're training this, right, you're going to need a data set that has corresponding videos with dense poses, and that's not difficult to do, right? All you need to do is you need to go, and if you're ByteDance, you have a bunch of data because you have TikTok, so you go and you scrape a bunch of TikToks, and for each of those TikToks, you break it up into individual frames, and then for each of those frames, you run those frames through a dense pose model, which is just some frozen pre-trained model, which will give you a dense pose given a image. And then in that way, you've now created a probably pretty big data set, if you're ByteDance, of images or of little videos, little TikToks with corresponding sequences of dense poses. And then you can use those to train this entire little pipeline here, right? Because you're going to need to know what the actual final answer is, or the actual final image is for each frame of that video. Okay. Pretty cool. So there's a lot of these papers, so I'm going to kind of blast ahead here. I think there was one more section here. Different from ControlNet, which adds conditions in a residual manner. We pass these features to the spatial self-attention layers in the UNet by concatenating each feature with the original UNet self-attention states to inject the appearance information. Okay, I think this was what I wanted to show here, is that a lot of these papers, so we're going to be going through a bunch of different video diffusion papers, but a lot of these papers are using this kind of core idea from ControlNet. So ControlNet is a paper that came out specifically for text to image diffusion model. So this is back in the day when we were still just generating single images. And what ControlNet did is it gave you a way to basically control, or like kind of like be more prescriptive about exactly how the image that is being generated by this diffusion model is generated, right? So specifically what a ControlNet does is it takes a specific type of control signal. In this case, it's a canny edge detected image. So similar to how you can basically just take any frame and feed it into some pre-trained model that'll output a dense pose. There's other types of models that are kind of similar like that, except this is not even a model, right? Canny edge detection, I'm pretty sure is just a hard-coded algorithm, but it'll give you basically the outline of an image, right? And then you can use that outline of the image. In this case, here what they're showing you is that you take the canny edge image, you feed it through an encoder, you get a latent, and then that latent gets used to control the diffusion UNet. So this part is within the diffusion UNet, and you can see here this little lock refers to the fact that you're not actually pushing any gradients or training or changing the actual diffusion UNet. Under the ControlNet kind of paradigm, what you're doing is you add a little extra little brain, right? It's like if someone took a little wire out of your brain and then put a little extra brain here, and then they only train that little extra brain. And that little extra brain starts from 0, so all the weights in the neurons of your little extra brain are initialized at 0, and then you just basically push some examples through, right? And by pushing those examples through, you eventually get this little extra brain that will be able to adapt the diffusion UNet such that it can now be controlled by an edge map, or an edge thing here, or any kind of like weird pose, or maybe a depth image, or maybe some normals image, or some other kind of image signal that is also being encoded into a latent representation in order to be used. But this idea here, this ControlNet idea, is pretty much all these papers are using some version of that. Okay, so that's the first one. How's it going, Ice? How's it going, Pain? We're going to jump ahead now to a second paper. So this paper is called Animate Anyone, also kind of end of November here, 28th November 2023. Consistent and controllable image-to-video synthesis for character animation. This is coming from Alibaba. So different Chinese company here. So you have ByteDance. That's the Chinese company that gave you TikTok. And then Alibaba, which is the Chinese company with the famous Jack Ma guy who was like secretly taken to some unknown place for a couple years because he was being naughty or something. I don't exactly know, but Alibaba is kind of like the Amazon, if you want to think of it that way. They started with kind of e-commerce, but of course now they kind of do everything. So this one also very similar kind of idea, right? Maybe let's look at a little bit of examples of these. And here we have examples of the Animate Anyone. Basically the same idea, right? You're using a pose sequence to animate a reference image. So you're going, it's image and pose sequence to video. So this is the same as this, right? Image and pose sequence to video. Except here, in this one, rather than using this dense pose format, which is a little bit more information dense, they use this key point skeleton here, which is a little bit less dense, but here it has a little bit more detail. So you can see this one has all the fingers, right? So I think that's why the hands look a little bit cleaner, because this type of control has all the fingers as well, right? Versus in this one here, these dense poses, the fingers aren't really there. They're just kind of like mittens, which is why it kind of doesn't look as good. Okay. But also kind of a side note, like these boys are thirsty. Like, you know what I'm saying? Like, it seems like all of these papers, like they use like borderline sexual content here, and like I don't know exactly what the situation is, right? I have not worked at like a Chinese AI lab, but like I gotta imagine it's kind of a weird situation if you're working at a Chinese AI lab and you're trying to publish a paper, and the senior kind of advisory person is like, okay, what examples we going to use? And they're like, here are the examples we're going to use, and it's a bunch of like sexualized girls dancing and like anime waifus, and it's like, who is rubber stamping this, right? Isn't that like a little creepy to be using these kind of things? But somehow it's getting through all of that, you know? Okay, so let's look at the actual system diagram itself, and then maybe kind of think about how it's a little bit different and a little bit similar. So we see here the same idea, how the reference image is being encoded with a VAE, so similar to this, right? You're encoding the image. Let's actually pull this up so we can look at it at the same time, right? You have a reference image and it's going into an appearance encoder, right? So that's the same thing here. You have here their VAE encoder is the same thing. It's encoding that, and then they're also feeding it into Clip. So Clip is a language image model that's been contrastively trained. And the point of Clip is that it's very good at kind of semantic knowledge, right? So it doesn't just like the representation that comes out of a VAE is ultimately that representation was trained using a loss that tries to reconstruct the image. So the VAE representation of an image is trying to really pack as much information as you would need in order to reconstruct the entire image, like at the pixel level, right? Versus Clip is not the same type of representation. Clip is more trying to tie together the caption associated with an image, such as a person wearing a gray vest with long brown hair, and the image itself. So Clip is going to have a different type of representation of that image than the VAE, right? Clip is going to be more of a kind of content or semantic, versus the VAE is going to be almost more like abstract, kind of like pixel spacey, high frequency. Okay. We also have our post sequence, so you can see here the little weird black triangle here. What that's referring to is that it's a bunch of frames on top of each other, right? You have a sequence of these frames, a sequence of pose frames. Here you also have the noise, so here similar to how you're encoding this sequence of pose frames, and then you're adding that to the latent noise, so that's the same thing here. You have noisy latents, right? Although here I think they're explicitly concatenating. And then you have a denoising unit. So this is the actual component of the diffusion model that actually removes the noise, right? Denoising, remove the noising. The way that the diffusion model is working, right? It removes the noise, but the way it actually works is it predicts the noise. So it predicts what the noise is at that frame, and then you remove the noise. And then it predicts what the noise is at that frame, and then you remove the noise. Okay? So you can see here the same concepts here. You have spatial attention and temporal attention. So the spatial attention is going to be with respect to the actual image itself, right? The frame within the frame, right? And that's going to drive the kind of appearance. Then you have temporal attention, which is the attention across the frames themselves. And that is about consistency over the whole video and consistency over time. Okay, the pose sequence is initially encoded using pose guider. Pose guider must be the some kind of VAE trained specifically on these pose skeletons, and fused with multi-frame noise. So multi-frame noise refers to the noise that you're going to use for each individual frame in the video, followed by the denoising unit, this part here, conducting the denoising process for video generation. The computational block of denoising units consists of spatial attention, cross attention, and temporal attention. So the cross attention, which is this blue, you can see it's cross attention between the actual image, cross attention between clip. So cross attention using the clip representation, which is the semantic representation. Temporal attention, which is going to be across the frames. Illustrated in the dash box, the integration of the reference image involves two aspects. Firstly, detailed features are extracted through ReferenceNet and utilized for spatial attention. Second, semantic features, I guess detailed features versus semantic features. Maybe that's a better way of describing it. So I was calling these like pixel space or high frequency features, but I guess detailed features is another way you could describe them. And then I was using the word semantic to describe the features that come through the clip. Temporal attention operates in the temporal dimension. Finally, a VAE decoder decodes the result into a video clip. Okay, so once you have what comes out of this denoising unit here is going to basically be a sequence of denoised latents, and you can take each of those denoised latents, feed them in through basically the opposite end of this VAE encoder here. So this VAE encoder here has a VAE decoder that's kind of been trained together, and you decode out the actual images, and then you can just concatenate them with FFmpeg and get the actual final video. Okay, so results here looking pretty clean again. They're all kind of obsessed with these TikTok videos. Okay, is there anything else from this paper that I highlighted? Not really. I think that was pretty much it. Okay, we keep moving. All right, so now we go to this paper here. This is a paper by Adobe Research called Generative Rendering, Controllable 4D Guided Video Generation with 2D Diffusion Models. So here, 3rd December 2023, so a little bit more recent, right? We're moving from this paper, and the release dates aren't necessarily indicative of when the work occurred. Kind of all of this work is roughly around the same time, right? 27th November 2023 to now. We're at 3rd December 2023, coming from Stanford and Adobe, so this is no longer a Chinese company. And this one is the same idea, but it's a little bit different, and it's different because it's using a 3D animation. So whereas these two used fundamentally 2D pose sequences, so dense pose here, it's fundamentally just a 2D control signal, right? This skeleton here, also a 2D control signal, right? But now in this paper, they're using a 3D control signal, and specifically they're using a 3D animation. So it's a little bit cheating, right? So it's using more information than these other papers, which is why they can get slightly better results. And if you actually look at their results, they do look better. Like for example, this fox running and these people dancing, it does look a lot better, right? But the problem is that you need this 3D control animated mesh. You see that? This is a 3D thing. So it's a little bit more, there's more signal there to basically extract, right? Versus these here are a little bit more crude. I think dense pose can't, like, there is 3D versions of these. There is 3D skeletons, but they're not as intense as this one here. Because this one has a mesh on it too. Okay. So let's look at the method overview here. So they have UV maps and depths. So a UV map is basically how a texture is wrapped onto an object, right? So in the mesh texture format for 3D, which is basically the format that people use nowadays in video games and CGI, you have two things to represent an object. You have a mesh, which is a series of vertices with little triangles, and then you have a texture, which is basically a RGB image, and that RGB image texture is basically wrapped onto the actual mesh. And the way that that wrapping is done is using a UV map, which basically tells you this part of the image texture needs to correspond to this part of the mesh, right? And it wraps over the whole thing. So this is kind of what I mean by they're starting from a more dense control signal, so therefore it makes sense that the final result is a little bit better. More data, yeah. Our system takes as input a set of UV and depth maps. So again, kind of a little bit more signal. So therefore, of course, it's going to be better. We use a depth condition control net to generate corresponding frames. So depth condition control net, again, same idea. They're using this kind of control net paradigm. let's go back here. While using the UV correspondences to preserve the consistency. We initialize the noise in the UV space of each object, and then we render it onto each image. So this is another little trick that they do here, right? Is that for these other papers here, right, they were the latent, or the noise that was eventually used as the starting point for the diffusion process was in the latent space, and it was basically, they're all independent. So you have independent noise for each frame in the video in a latent image space, right? In this one, they actually now do a little bit of a trick, right? And the trick is that the noise is in the UV space of the object. So by initializing the noise in the UV space, that means that the noise is like almost, you could think of it like it's glued onto that specific part of the original or kind of like control signal, right? So here they have the little fox running, and the noise is kind of, you can see here, they kind of try to show you with these maps, right? It's kind of like glued onto specific parts of the fox or specific parts of the background. And that little trick allows you to basically have a little bit more consistency on the individual frames, because when you think about it, right, you have this fox running, right? And this fox running is really a sequence of frames, and each one of those frames started from some noise, but the noise that was used to initialize, for example, maybe this tail is the same as the noise that was used to initialize this tail in a later frame, right? Because both of them were starting from the same noise, which was mapped onto that UV map, which goes onto the mesh. So it's a neat little trick that allows them to get that little bit of extra consistency, which you can see kind of the difference, right? For example, here, like, I don't know, I'm trying to pick an example here, but you can see, like, you see how the relative position of like this like black band on the t-shirt, it stays, right? Like, or this tie, right? That tie is a little bit more consistent, even if it moves kind of back and forth across the entire video, right? Because it's corresponding to the same part of this UV map, which is ultimately going back to the same noise, right? So they call this unified initial noise. Okay. For each diffusion step, we use the extended attention for a set of keyframes. So keyframes here refers to the lower frame rate. Again, most of these techniques are working at a low frame rate, and then they basically fill in to the 30 FPS required to get the nice demo. And extract their pre- and post-attention features. The post-attention features, this is the features after the attention block, and then the pre-attention features would be the features before the attention block. Are projected to the UV space and unified. So again, the same kind of trick of really leveraging the fact that you have a full 3D model of the whole thing, right? You have this depth and UV map prior, so you might as well just kind of leverage it for everything that you can. So they're also going to be mapping these attention features to that. Finally, all the frames are generated using a weighted combination of the outputs of the extended attention with pre-attention features of the keyframe and the UV-composed post-attention features from the keyframes. Okay. So here you have a little bit of a self-attention block, right? The attention mechanism here has a couple different pieces in it. You have the queries, you have the keys, and you have the values. So the way that attention works, the queries and the keys are basically doing dot products with each other, such that the queries and the keys that are kind of most in the same direction end up with high values, and then the queries and keys that are in opposite directions, if you think of them as a vector, right, have low attention or zero values, right? So high activation means that the keys and the queries are both basically saying, yup, queries like this is what keys are this is what I have, and then queries are this is what I want. So basically it's an agreement between this is what I want and this is what I have, versus low value there would basically mean that it's not what I want, it's not what I have. And then the value is the actual value that gets basically passed to the next attention block, next layer, right? And that's actually more, you're modulating that by how much agreement there is between the queries and the keys here. Okay, but they're doing this with these features which are mapped onto that UV map. So you can see here, for example, the pink stuff corresponds to the background. This blue stuff corresponds to the fox. So the fox features are always kind of constrained to pay attention to the other fox features. So it kind of makes this whole thing a little bit better. But with that said, I feel like there's a big problem with this. And the big problem with this technique is that you need this input, right? You need this perfect mesh UV map depth input. And that's not always going to be the case, right? If you are working in a 3D world, like in Blender or in Maya or in any Unreal Engine, any of these type of game engines, right? You're already working with 3D primitives that are already in texture and mesh format. So if you're in that world, then hey, you might as well use that, right? But I feel like that stuff is going to eventually go away. So once these type of explicit 3D representations where you have meshes and textures and UV maps, once those things go away, then these techniques like this paper that are depending on that type of intermediate representation, intermediate explicit 3D representation in order to basically more efficiently condition video generation, they're also going to disappear. So, you know, the reason this sneaker here, this black sneaker and this blue sneaker, the reason they look so good is because this is perfect, right? Look at this input. It's literally perfect because you have the actual 3D model of this sneaker. So, yeah, that's this paper. It's basically the same idea of using ControlNet to basically animate images, but where the images can come out of a diffusion model. But in this case, they're using kind of weaker control signals like the dense shape and these pose skeletons, versus in this Adobe paper, they're using that much stronger control signal of like a 3D mesh with a UV map. And that's why they get slightly better results. Okay, so now we move to a slightly different type of control. Wait up. I see questions. Adding a 9th channel was big. I would reconsider the 3D as being a new fundamental requirement instead of cheating. Yeah, I mean, with all these things, right, it's like I'm not 100% certain, right? So whenever I sit here and I pontificate that in the future we're never going to use these explicit 3D formats like meshes and textures, that's just me pontificating. You know, I don't actually know for sure. It might be the case that we always end up using these 3D formats because we figure out ways to create those 3D formats, right? So, I don't know. Could go one way, could go the other way. I'm just giving you guys my opinions, right? And then Josh Phillips, couldn't you just use splats to generate the 3D info from 2D? Yes, you could probably create some kind of technique very similar to this where you are using the splats, right? Splats are basically a collection of, it's kind of like a point cloud, right? So when you have a Gaussian splat scene, you have kind of something that looks like this, right? You have like a depth. It's not going to be as clean as this one because this is a depth that comes from a mesh in a 3D scene where everything is basically 3D explicitly. It's going to be probably a little bit more noisy, but you do have that. You do have the notion of a depth image and something like a UV map in a Gaussian splat. So you could basically recreate this entire paper using a Gaussian splat as kind of the control signal. But I don't know if that's necessarily the best way to do it because the progress moves very quickly, right? And these complicated pipelines that rely on a bunch of intermediate things, usually the way it works is those pipelines basically disappear into the fog of history and someone comes up with a more general method that doesn't have as many different intermediate complicated steps or inputs that works even better. So the computer vision usually works in this kind of way where there's this kind of push and pull with complexity where like something comes out, people make increasingly more and more complicated versions of that pipeline that use increasingly stronger and stronger different inputs or control signals, and then eventually someone comes up with a new way to do things that is usually more data-driven, more kind of bitter lessony, that simplifies it, doesn't use all this extra information, and then that's the new paradigm. So, okay. But, okay, back to this paper. So motion control. This is now 6th December 2023, so we're getting pretty close to current date. This is a unified and flexible motion controller for video generation. This is coming from Tencent, so another Chinese company here. So we have basically full representation from all the Chinese tech giants here. We have ByteDance, we have Alibaba, and now we have Tencent. So those are basically the big Chinese tech companies. And maybe just like a meta comment here, like people talk about the US being ahead in AI, but that is not the case, right? Reading these papers, like it seems like really like most of these papers are coming out of Chinese companies, and a lot of the kind of state of the art is coming out of these Chinese companies. So especially in the computer vision space, I feel like China is ahead of the US when it comes to computer vision. It might not be ahead of the US when it comes to language models, and even I would say that there's probably an argument to be said there, but I don't think we're operating in a world where the Chinese tech and AI ecosystem is behind the American and kind of more Western tech AI ecosystem. I think, if anything, like more and more, I'm looking at these papers and they're almost always Chinese papers, so something to think about there. Okay, so in this paper, they're basically going to be conditioning the video generation on camera trajectories and object trajectories. Okay, so let's look at this. Existing works, blah, blah, blah. This paper presents Motion Control, a unified and flexible motion controller for video generation designed to effectively and independently control camera and object motion. So independent control of camera motion and object motion. The architecture and training strategy of motion control are carefully devised, taking into account the inherent properties of camera motion, object motion, and imperfect training data. Compared to previous methods, motion control offers three main advantages. It effectively and independently controls camera motion and object motion, enabling more fine-grained motion control and facilitating flexible and diverse combinations of both types of motion. Its motion conditions are determined by camera poses and trajectories, so a sequence of camera poses, right? Same as you have here a sequence of poses, in this case dense poses. Here you have a sequence of skeletons, right? Here you have a sequence of UV maps and depth, and here you have now a sequence of camera poses, right? So you can see here each of these little triangles represents a camera, right? And you can see how you basically have motion of the camera. So it like kind of moves forward and then it kind of does like a little pan like this. And that's kind of the exact effect that you see there, right? So all of these are basically conditioning video diffusion with these control signals. In this case, now we're looking at camera motion, which are appearance-free and minimally impact the appearance or shape of the objects in generated videos. So the control signal that they're using here of camera poses are appearance-free in that they don't want the motion trajectory of these cameras to mess with the appearance of the actual images. It can adapt to a wide variety of camera poses. Extensive qualitative and quantitative experiments have been conducted to demonstrate the superiority of motion control over existing methods. So they don't claim state-of-the-art, but this is like a weird sentence. This is almost like a politician sentence. Like, you know what I'm saying? It's like they're trying to claim state-of-the-art without actually saying the word state-of-the-art, because that wouldn't be allowed unless they actually got state-of-the-art. So what exactly does extensive qualitative and quantitative experiments have been conducted to demonstrate the superiority over existing methods? Right? Like, that seems like such a weird 500 IQ way to try to say state-of-the-art without saying state-of-the-art. Okay. This paper does start from a latent video diffusion model, actually, so this paper was in 6th December 2023, and if you actually, I pulled it up here, but this is another Tencent AI lab, and I actually highlighted, there's a couple people in common here. So you have Yong Zhang and Ying Shan from Tencent AI lab. Those are the same Ying Shan, and actually maybe not this guy, but it's the same Tencent AI lab. So basically you have a group of people at Tencent who worked with, for example, Hong Kong University of Science and Technology. And here they worked with Tsinghua University, Shanghai University. So it's similar to kind of the way that the American system works, where basically you'll have like an industry partner, and the industry partner is probably providing the compute, the money, and a little bit of kind of the project direction. And then you have an academic group that provides the actual people, right? The actual interns, researchers that are going to do the actual work. So these first two names here, right? These are the people who actually did the work. The names in the back here, these are kind of the advisory roles. So you can see here how the people at the Tencent AI lab are kind of in the back here. They're kind of doing the advising, giving them the money to actually run the things. But then the actual people doing the work are students from Hong Kong University or students from Tsinghua University. Okay. And this is an early paper, so this is the latent video diffusion model that they use is actually quite old. This is from March 2023, so earlier this year, and it's really not that great, so you can kind of see the quality. It's a little bit primitive, but for a early 2023 video diffusion model, pretty good, right? So that is what they start from. The latent video diffusion model aims to generate high-quality, diverse videos. It employs a denoising diffusion model, aka UNet, in the latent space. So latent diffusion models, latent video diffusion models. Okay, blah, 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 blah. And then we get to the system diagram here. So the system diagram here is not quite as pretty as the other ones, but let's go ahead and get started here. So we have a man rises a horse in Mars. So always kind of funny to read these Chinese papers because they'll have like typos. I think here this is supposed to be a man rides a horse in Mars. So I don't think rises is the right word there. So I hope that's not what they put into their clip encoder, because then the clip model encoder is going to be incorrect because the difference between the word rise and ride is actually quite big. So that would have completely fucked up their pipeline if that's what they used. So hopefully that's not what they used, but maybe it's just a typo in this figure. They use the prompt, put it into clip, then that clip, you can see here this dotted blue, is used to basically condition, and you can see here how it's conditioning all along the denoising UNet, right? The UNet is taking this latent here, and then it's outputting another latent that is denoised, right? And then you would then take that denoised latent and then feed it through the decoder that you used for your image space to latent space, and then you would get your final image space, spatial transformer. So you can see here how the spatial is within individual frames, right? So that's going to be the appearance. So you can see here how the clip is only used to condition the blue, which is the spatial transformer, which is basically the appearance of the image. Then you have this green here. So this green is the temporal transformer, which is the frames across the video, so the time dimension. And you can see here how the temporal part is being conditioned on this green stuff here, which is the camera pose. So a sequence of camera poses is a sequence of rotations and translations. So here RT0, RT1, that's the rotation of the camera at time step 0. The T is the translation or the position of the camera at time step 0, right? So RT1 is the rotation and translation of the camera at time step 1. RT2 is the rotation and translation of the camera at time step 2, and so on, right? And here they have this little yellow part here. They call this CMCM, which I think they call it Camera Motion Control Module. So the Camera Motion Control Module, you can see here it starts from this RT, which is the camera position. This is the dimensionality of RT. The dimensionality of RT is B, which is the batch dimension, right? So when you're training these, you're doing it in a batch, right? You're not just feeding one image at a time through your GPU. You're feeding a batch of images through your GPU. L, what is L? L might be the length. Yeah, L denotes the length of the generated video, so basically how many time steps you have. Then 12. So where does this 12 number comes from? 12 comes from R and T. So a rotation, one way to represent that is a quaternion, which is 4 numbers, but a more explicit way to represent that is a rotation matrix, which is a 3x3 matrix, which is 9 numbers total. And the T part here, right, that's a translation, that's another 3 numbers. So if you want to represent this R and T, you need 12 numbers total. You need the 3x3 or the 9 numbers that represent the rotation, and then you need the 3 numbers that represent the translation, which is in total 12. So that's where this B by L by 12 dimension comes from. Here, YT, this is basically whatever's coming out of the previous layer. So X generally denotes the input, and then Y denotes the output. So you can see here, I guess here they're calling it Z. Is there an example where it's Y and T? Not really. Okay. But the dimensionality of this YT, right, it's going to be batch by length, but this time by height, and then width. So now we're in latent space, and then C, which is channels. So how the latent space is going to have more channels than just 3, and then the H and W is going to be less than the size of the original image. Okay, so they reshape these so that they can concatenate them. Then they have a fully connected layer here. That little fire there refers to the fact that it is trainable. So they are pushing gradients, and they are basically training this CM, this little control module for specifically the camera pose over this process. And then you have a little attention block there. Okay, and then I think the last part of this system diagram that we need to think about is this part here. So here they have trajes. Trajes is what they're using for object trajectories here. So the camera poses are 12 numbers that represent a camera position and rotation over a sequence of L frames. A object trajectory is kind of more similar to this, where it's basically a 2D control signal, where it's basically just a 2D position in pixel space over a sequence, same amount of frames. But because it's different from the camera kind of control signal, they have a separate module, which they call the OMCM, the object motion control module, which is going to condition here the UNet as well, specifically the conv layers of the UNet. Okay, so let's see if there's anything else in this paper that I highlighted. Trajectories for object motion control. Okay. 8 NVIDIA Tesla V100s. Pretty cool. What else? I don't think there's anything else. Largely, actually, why don't we look at the results a little bit? So here you have the results, right? You can see how the camera motion, you can effectively control the video diffusion model. You see that, how it's basically following this camera motion. The video diffusion model isn't great, but it's also because they're using this video diffusion model, their Tencent video diffusion model, which is quite old at this point. So don't think too much about the quality, think about the actual motion of the camera. That's kind of the more impressive part. So here the motion of the forest, and then they actually show you that they can combine both of them. So here that was camera motion control, this is object motion control. So you can see here how like a little loop like this in 2D pixel space trajectory moves the little wind chime. You can see here this paper plane follows this kind of like up and down sinusoidal trajectory. It's pretty good. It even gets little details. So if you notice here, for example, look at how the wing part of this paper airplane kind of like does this kind of like almost like a wave, right? Like that. That's pretty next level. That's just emergent video magic, you know what I'm saying? That's not they're not explicitly controlling every single part of this paper plane. Really, the trajectory for the object is just a 2D, it's a single point. So it's quite impressive that you get those kind of weird second order effects just naturally. Here you have, for example, 2 zebras moving past each other, 2 cats moving past each other, and then here they have a combination of those. So you can use both the camera control module and the object motion control module in tandem. So here you have a camera motion, which is zooming out in tandem with a kind of the rows kind of moving back and forth. So pretty impressive stuff here. Look at these. Pan out, zoom in, pan left, pan right. This is pretty good. The one thing that I don't like about this is that much like these, right, I just don't like this control signal. I don't think this control signal is super useful because who the fuck has this, right? Like, do you have a do you have a camera pose trajectory? Is that something that I can just sit there and write? No, I don't have that, right? Do I have a object trajectory? No, I don't have that. It's like, I want to be able to describe this camera pose with text, right? So I want to be able to say, pan out, pan in, right? Like circle around, like I want to be able to provide my control signal in the form of text like this, right? Having to provide the control signal in the form of a camera trajectory is not a great workflow, because unless you're already in a 3D tool such as Blender, you're not going to be able to provide a camera trajectory like this. So similar to this, where you get good results, but the control signal requires having all this explicit information, I think this one suffers from the same problem, where it's great results, but having to use a camera pose trajectory and an object trajectory makes this not very usable, versus if you just went an extra step and basically went from text. Maybe you create a separate model that goes from text into camera trajectories, but I feel like that would have been kind of that would have taken it just that extra little step that it needed. What else here? Latent video, denoising UNet. I think there was one more thing here that I wanted to talk about. Maybe not this one. I think it might be the next paper. Okay. Let's take a little coffee break, and then we'll go into the next paper. Let's turn on the robot for the coffee break. Let's see if you guys have any questions here. Can you tell me from which paper explains that the diffusion does not require the forward process of adding noise?
Sure, I can tell you, but remember, my memory's like a sieve.
He's answering my questions. Hey, over here, look at my hand.
You're welcome. Just don't ask me to remember. My brain ticks like...
Can you wave at me? Wave at me.
You're welcome. Just think of me as a goldfish with a stopwatch.
Wave at me. I think he already died.
Memory? I'm like a sieve in a time trial.
Okay. So now, this next paper, we're moving forward in time, 6 December 2023.
Got it, human. I'm the haiku of tech, brief and precise.
Also from Tencent. So you see some of these same people coming back. So Yong, Zhang, Ying, Shan, same people's here.
Tencent's cousin, am I? A digital poet, memory fleeting.
Tencent's cousin. Ying, Shan, Yong, Zhang. So same kind of advisory people, but now, right, the people doing work, this guy here, Jiwen Yu from Peking University here. So very interesting kind of technique here, just kind of like as a meta point, where Tencent is working with all of them. They're working with Tsinghua, Shanghai, all these different universities, which are basically all over China. They're basically working with all of them, which is kind of interesting, right? It's not like you have a kind of a one-to-one situation. It's like they're basically, Tencent works with all of them, kind of exploits that cheap graduate student labor, I would suppose. Okay, so these boys also a little bit thirsty. All their examples are basically cat girls and anime waifus, but, you know, I guess you got to grab attention any way you can. And this one is a little bit different from the previous paper. So this is now a text-to-video diffusion model. So there's no control signal apart from the original reference image, right? So in all of these other papers that we were looking at, there's this control signal, such as the dense pose or the skeleton or the UV maps and depth maps or the camera motions, right? In this one, there's no control signal. You're just literally making a video from a 2D generated image. Okay. However, the generation process is still a black box, where all attributes are learned and generated jointly without precise control ability, inspired by image animation, which couples the video as one specific appearance in the corresponding motion. We propose Animate 0 to unveil the pre-trained text-to-video diffusion model Animate Diff, and provide a more precise appearance and motion control capabilities for it. For appearance control, we borrow intermediate latents and their features from the text-to-image generation for ensuring the generated first frame is equal to the given generated frame. And this is kind of both the blessing and the curse of text or image to video or text to video models, is that they have a very strong kind of appearance bias to that first image, right? So if you notice all of these videos, there's not a lot of motion here. It's basically the same subject in the same background, and like the appearance of that very first frame to the very last frame is a very high. There's a very high kind of match there, right? So there's a very strong kind of appearance signal coming from the fact that you're using a bunch of techniques to ensure that every frame in that video is consistent with the very first frame or the reference frame of that video. But the problem with that is that then it becomes a curse, right? Then the problem is that you can't really have more complicated motions, more something where like the subject switches or the background switches or the lighting switches, because you have all these parts inside your pipeline that are pushing every single frame to be consistent with that first frame and the previous frame. So that's kind of the blessing and the curse of like the strong appearance constraints that ensure that the generated first frame is equal to the given generated image. For temporal control, we replace the global temporal attention of the original T2V model with our proposed positional corrected window attention to ensure other frames align with the first frame as well. Empowered by the proposed methods, Animate 0 can successfully control the generating progress without further training as zero-shot image animator for given images. Animate 0 also enables multiple new applications, including interactive video generation and real image animation. The detailed experiments demonstrate the effectiveness of the proposed method in both T2V and related applications. So they're not claiming state-of-the-art, but they're also kind of like vaguely saying that it's good, right? So Chinese AI papers and very vague sentences that try to say that they're very strong without saying that they're very strong. Okay. We scroll down to here. What did I have here? There have been some attempts to move towards image animation. Publicly available tools include Gen 2, Genmo, Pika Labs. Should we bring up Pika Labs? Yeah, let's bring it up. Pika Labs. You guys probably saw this, but this was a startup that released this kind of video here where they were basically showing their text-to-video model, and they have this kind of like Gemini-esque demo where like they cut really quickly and like they don't really show you for very long because, you know, like if they showed it much longer, you would be able to pick out the details. So they're kind of being a little bit misleading here by trying to make you like, oh, you're too focused on the whole thing to even realize that there's mistakes in this video. So yeah, I don't know if it's necessarily state-of-the-art. I think they're all kind of about in the same place. Gen 2 as a commercial large-scale model delivers impressive results in the realistic image domain in its November 2023 update. However, its performance in other domains, which may not have been covered in training, is also still not entirely satisfactory. Okay, so, right, this paper has a bunch of anime examples, so kind of what this is telling me is that the person who made this paper is obsessed with anime, and they went ahead and they tried to generate anime with Pika Labs and Gen 2, and then they were like, this thing is garbage at generating anime, so that's kind of what they're roughly telling you there. Okay. Spatial motion. All right, this is what I want. Okay. So now we have the system diagram for this Animate diff. The overall, or Animate 0, sorry. The overall pipeline for our proposed Animate 0. Given spatial modules from a pre-trained text-to-image model, so a pre-trained text-to-image model is going to be something like a Stable Diffusion, and its corresponding motion modules. The motion modules are going to be specific to text-to-video. We first generate an image I using the T2I model, and then generate a video animated from this image, step 2. Okay, so step 1, you basically generate, using a standard pre-trained diffusion model, an image from some text. And you can see here how you're iteratively denoising. So here you start with pure noise, and then eventually you remove the noise, and you would get the actual final image. Okay. The left part shows the image generation process with the intermediate latents and our proposed spatial appearance control. So intermediate latents, what they're referring to is that when you're generating this image, right, you're using first of all, you're not generating an image space, you're generating in latent space. And when you're generating in latent space, you're going to be denoising for for a couple subsequent steps in latent space. And each latent, as you denoise, you're going to have a sequence of those, right? From time step capital T to time step 0. And that you're going to basically, that's what the intermediate latents are. They're basically the intermediate denoised latents that come out of this denoising UNet as it slowly denoises towards a final latent, which then becomes the final image. Okay. The spatial appearance control, right? So controlling the video model with spatial appearance, right? Spatial appearance within the image, and mostly you're concerned about the actual look of the thing. Makes modifications, including their latent insertion for ensuring the first frame equal to I1 and sharing keys and values from the spatial self-attention of the first frame across other frames to align both semantics and styles. Okay, so this starts to get a little bit more complicated here, but you see here these KV and here the KQ. So this means the keys, the queries, and the values, right? So this is basically, if you remember how we were saying that attention mechanisms, attention blocks, basically have three basic parts. They have the keys, the queries, and the values. So here, what they're referring to is that, for example, K11 is the ith token with the jth position embedding, where the position embedding corresponds to within the video. So you have position embeddings being used spatially, right? So there's position embeddings so that your vision transformer, in vision transformers, when you're looking at an image as a sequence of image tokens, right? Those tokens, the way that the vision transformer knows where in the image those tokens are is because there's a position embedding that's telling it where in the image it is. But here they also have position embeddings for the the temporal dimension as well. Okay. But in-frame similarity, so what are they referring to here? They're saying that, okay, if you look at an attention map, the attention map is basically saying a sequence paying attention to another sequence, right? So self-attention, you have one sequence paying attention to the same sequence. Cross-attention, you have one sequence paying attention to a different sequence. So here, this green part, we're inside a self-attention block, which means the sequence is paying attention with itself. And inside this self-attention block, right, the diagonal here is going to correspond to the query for the first token and the key for the first token. So the dark green means it's basically the same frame paying attention to that same frame, right? Versus these light greens, right? Because you're looking at this as a sequence of video frames, now these light green frames are cross frames. So the attention scores in these light green are going to basically correspond to attention between two frames in the video, versus these dark greens, this is going to be attention between the frame and itself. Right, same frame, in frame they call it. Okay, and the kind of trick that they use here, so here they're calling this global attention, and this is Animate Diff, which is an earlier version of their work. I think we actually did a stream on the Animate Diff paper, but they do this trick which they call positional corrected window attention. Okay, and you see the trick that they did here is that they basically copied the very first the keys for the very first frame, right? So you see here how it says shared KV. So another way to think about this is it's like a KV cache, right? So in the language world, when you're using an LLM, you have the prompt, and then the prompt is encoded, and that encoded prompt is then cross-attentioned within the decoder to the output, which auto-regressively generates one token at a time, right? And by caching those K and V values, you can save a lot of compute. So there's a similar kind of idea here, except now what you're doing is you're duplicating the keys that correspond to that very first frame. So again, if you remember, right, the whole point of this technique is that everything is paying attention to that first frame. You want every subsequent frame in this video to be very, very basically similar to the very first frame of the video, or the very first image in that sequence, or latent in that sequence of latents. So that's effectively what they're doing. They're saying, we're going to basically make every part or every subsequent frame pay attention to that very first frame. And that's what they're doing here. And we're going to do that by duplicating that first frame. So that's why you get K1, 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 K1 here, and then K2, K3, right? But then by the time that's at the very beginning, right? So the second frame is almost like it's paying attention to, if this is a 10 frame video, it's paying attention to 9 frames that are the duplicated first frame and then itself, versus the very last frame of the video is paying attention to all of the previous frames. So as you go through the video, the strength of how much that very first frame matters is decreasing, right? The very first frame matters a lot more in the early frames, because just see how many more yellow bricks there are here compared to the very last frame. The very last frame doesn't have as much signal coming in from that very first frame. Okay, this gets pretty complicated. I don't know if people are lost here, but just remember that everyone's lost. I get a little lost on these things too, if not a lot lost. Okay. Right part is the temporal consistency control. We propose modifications to the original self-attention, which is a global attention. Our modification includes 3 points. We replace global attention to window attention, which computes the ith output token only for using the preceding I frames. And we duplicate the similarity computed with the first token to emphasize the importance of the first frame. We correct the position embeddings marked as red, and the calculation of QKV is described as added to the input tokens to get better results. Okay. I think there was one other cool thing that I saw here in this paper. Was it this one? So this is position corrected window attention. There was one cool thing here. I thought it was this one. Oh no, I think it's this one. Okay. All right. So is there anything else we need from this paper here? Not much. Okay, so in terms of like the final result here, again, I think they're okay, but I don't like the fact that you're limited to something that is extremely stationary and flat. There's just, you're lacking kind of the dynamicness of like something like this, right? Like this is really where I feel like we're pushing the limits of video diffusion. Like this is not, these kind of like just little tiny animations like this, like it's not complicated enough for me. Okay. Now, let me take another little sip of coffee here. Now we're going to move into Dream Video. Okay, so Dream Video is a paper 7th of December 2023, so we're moving forward in time here. And this is coming from Alibaba, so same group over here, right? Same kind of recipe where you're basically taking kind of advisory type people from Alibaba and then some more academic type people which are actually doing the work. So in this case, the academic type people are from Huazhong University of Science and Technology and Fudan University, and then Zhejiang University, and then Alibaba's paying the money. Okay. So customized video generation requires the ability. We present Dream Video, a novel approach to generating personalized videos. Why is this strike through? I want highlight. A novel approach to generating personalized videos from a few static images of the desired subject and a few videos of target motion. Dream Video decouples this task into 2 stages, subject learning and motion learning. By leveraging a pre-trained video diffusion model, the subject learning aims to accurately capture the fine appearance of the subject from provided images, which is achieved by combining textual inversion and fine-tuning our carefully designed identity adapter. In motion learning, we architect a motion adapter and fine-tune it on the given videos to effectively model the target motion pattern. Combining these 2 lightweight and efficient adapters allows for flexible customization of any subject without any motion, or with any motion. Extensive experimental results demonstrate the superior performance of our Dream Video over state-of-the-art methods for customized video generation. Okay, so they do actually mention the state of the art here, but I don't actually think this is state of the art. If we actually look at these videos, they're a little weird, you know, but they're also more challenging, right? Like this type of video is just kind of fundamentally more challenging than something like the Animate ones, right? Like this is kind of an easier problem, IMO. But I think also the control signal is much better, right? So here, the control signal, you have two different types of control signal. You have what they're calling the subject control signal, which is kind of like the appearance or the thing that's actually in there, right? So in this case, you have a couple pictures of a sloth, a couple pictures of this monster, right? That's a very natural control signal, right? Compared to the other stuff that we were looking at with these unnatural control signals like camera trajectories and pose skeletons and things like that. So this is, I think, a much more realistic type of control signal. And then you have a motion control signal, which is a video of here, for example, a person playing a guitar. So you're basically combining these two in order to generate a new video, which kind of says this dog in this video, this sloth in this video, this monster in this video, right? And it's a little weird. Like there's definitely some weirdness going on here, but pretty good. You know, like look at this. You got the dog lifting the barbell. Sloth lifting the barbell. Monster lifting the barbell. It's not quite there, but I think these control signals are harder to use. Okay. So let's dive into this one. It's this one. Okay. Boom. Jumping right to it. Illustration of the proposed dream video, which decouples customized video generation into two stages, a two-stage pipeline here. In subject learning, we first optimize a unique textual identity for the subject. So subject learning, you're taking pictures of this dog, and you're getting this, you're kind of, I think they describe it here better, perfect. Subject learning, blah, blah, blah. Textual inversion. You see this? Textual inversion. So this term here. What is textual inversion? Textual inversion is basically saying I'm introducing a new concept to a diffusion model where I'm assigning a specific kind of subject or like appearance of this dog to a specific token, but then I'm pushing the gradient only into this little adapter here, right? So what you end up with is something that basically knows what that little new token means, right? So dog star, you're basically saying this dog star, of course, this text token corresponds specifically to this dog star, so that then if you put this little adapter here in a video diffusion model now, and then you have a dog is playing guitar, this dog star, it knows what it corresponds to because of this, the information that you put in here, basically, the juice that you put in there. We then train the devised identity adapter with the frozen textual identity to capture the fine appearance details. In motion learning, we pass randomly selected frame from its training video through the clip image encoder and use its embedding as the appearance condition to guide the training of the designed motion adapter. Note that we freeze the pre-trained diffusion model throughout the training process. So they're not, in order to get the subject, what they're calling the ID adapter, the like appearance, and then the motion, which they're calling the motion adapter, right? And these little adapters are basically, in this paper, they're actually little LoRa's, which is actually kind of cool. But we'll go into actually, why don't we just go into that? So these adapters here, right? So they have their subject adapter, ID adapter, this little orange brick here. Here you have your video diffusion model, which is a 3D UNet. Here you have your motion adapter. You can see here how the motion adapter, this is a little bit more, you can see here how the ID adapter is only modifying what's going in and out of this cross attention module. And then the motion adapter is modifying what's going into this self-attention module, and the FFN, which is the feed forward network, which is the kind of like a little layer after the attention modules, like a little fully connected little neurons there. Okay, but the cool thing which I discovered about this is that these little adapters are basically like little LoRa's, right? So here we have figure 3, illustration of the devised adapters. Both use bottleneck structure. Compared to the identity adapter, motion adapter adds a linear layer to incorporate the appearance guidelines. Okay, so they're kind of similar, right? You have a little residual connection here where the signal that comes in here just gets concatenated at the end. That's a residual or a skip connection, pretty common kind of architecture little feature. And then you have this W down and this W up. And when I saw this, I was like, that looks a hell of a lot like this, right? So this is a LoRa. This is a low-rank adapter. And this is a type of adapter used for fine-tuning. Very popular in diffusion models, also popular in language models, and even used for things like bio. But the way that these adapters work is that you initialize them from 0. So here you see this N stands for a normal distribution, Gaussian distribution, centered at 0 with some variance, sigma squared. But and then basically you keep this part frozen, and then you add this little adapter, and then you train it, fine-tune it on your special little mini data set, which in this case is the specific subject, right? So the specific dog. And then you only push gradients into this, and then you can take this and merge it in if you want, or you can just treat it separately if you want to do that as well. But the reason these LoRa's work is because the dimensionality of this R is much lower than the dimensionality of this D here. So basically, the full pre-trained weights, which are a D by D weight matrix, is way bigger than these LoRa's, which even though it's 2 matrices, it's an A matrix and a B matrix, it's a D by R, R by D matrix, which ends up multiplying to the same D by D, but because this R is smaller, it's a whole lot less numbers. And the same thing is here, right? If you actually scroll down here, subject learning, blah, 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 leverage, blah, 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 and then here you go. As demonstrated in figure 8, the identity adapter adopts a bottleneck architecture with a skip connection. So this is the little skip connection here, this little black line which goes up here. And then they say, consists of a down projected linear layer with weights W down, L by D, a nonlinear activation function sigma, and an up projected linear layer with weight W up, D by L, where L is greater than D. So there you go, the same kind of situation where you're leveraging the fact that if you use an L that is, I guess here they have, it's bigger, but like by using, I guess maybe it's not at all. For some reason, when I read this morning, I thought they were going to say L is less than D, but L is greater than D here. So this is not like a LoRa at all. And it's also got this nonlinear layer here, right? So there's a ReLU or something here versus here, there's nothing, right? There's no ReLU here. You just go straight from A times B versus here, you have this activation function in between here. So maybe I was wrong, right? I thought that for some reason when I read this, I thought this was L less than D, but oh, no, I am correct. Okay, never mind, sorry. W down is D, then L, then D. No, it's L by D. Oh my God. All right, so it's flipped. You see this? This is D by D, so the dimensionality is D by R and then R by D. But in this paper, they actually use different notation, and D is the inner dimension, because this is L by D and then D by L. So L is bigger than D, which means that this outside here is bigger than inside here, which is exactly what it was in LoRa. Okay, so I was correct. It's just that they switched, and they're using the letter D to describe the inner dimension, not the outer one. Okay, that was a bit confusing, but TLDR, these little adapters are basically like little mini LoRa's, or similar to LoRa's, except they have that nonlinear in there in between. Average weight change in spatial weight change rate in spatial parameters, average weight change rate in temporal parameters. So mean delta. So what do they mean here by weight change? So any neural network, right, and a video diffusion model is one of these, right? It's just a series of parameters. It's just a bunch of parameters, and each of those parameters is like a little value, right? So it can be like 0.1 or 1.3 or something like that, right? So whenever you're pushing gradients with a learning rate, really what you're doing is you're ever so slightly changing the value of those little parameters, right? And here they're basically telling you how much do the parameters change at each of the different parts of this video diffusion model. So temporal versus spatial. Spatial is within the frame. Temporal is across frames in the video. You can see here how mostly what's changing here in the spatial is the cross attention versus self-attention here in the temporal. I mean, that makes obvious because they're literally putting this right here on the cross attention, so I don't know what they were trying to say by that. Cross attention layers play a key role in subject learning, while the contribution of all layers are similar to motion learning. Okay, sure. All right. But now, once you have this ID adapter and this motion adapter, you can then take a pre-trained video diffusion model, right? It's frozen. You just put in these little ID and motion adapters. You start from a sequence of noisy latents, right? So actually very similar to all of these, right? You start with this sequence of noisy latents here, sequence of noisy latents here, right? Noise. Here in this one, sequence of noisy latents. Where is it? Here we go. Initial noise. Here they actually do the unified initial noise, so it's a little bit more tricky, but same thing. Start with a bunch of noise. And then you basically condition on these two things, and that's basically it. And you end up with that. End up with a video. Pretty cool. Video diffusion models. Was there anything else in this paper? I think that's pretty much it. Okay. Ultimately, we're already at 9:30. Okay, I don't have as much time as I thought I did, but this is where I wanted to end the stream because this is what I think is the state-of-the-art video diffusion model, right? So this stream is all about video diffusion models, but so far we've mostly just been looking at papers where they're using basically a control net kind of paradigm to use a control signal to basically do image to video or text to video. But in terms of pure image to video, text to video performance, I feel like the stable video diffusion model is like the king. Like these look so good, right? I don't know about you guys, these look fucking amazing, but available on Hugging Face. And this is the paper. Stable video diffusion, scaling latent video diffusion models to large data sets. And here we have, I highlighted some of the people here. So Stability AI is the actual company, right, that makes the stable diffusion models. You have Andreas Blattman, Tim Dockhorn, and Robin Rombach. And actually, those people come from this earlier paper, 18th of April, 2023. And this was before they worked at Stability. So here you have Andreas Blattman working for LMU Munich, in addition to Robin Rombach and Tim Dockhorn working for NVIDIA. So you can see here how basically these three people here who made a very early video diffusion model, right, in this case, 18th of April, 2023, basically got poached by Stability AI and are now basically the people behind stable video diffusion. So that's how that works. Let's see. We present stable video diffusion, a latent video diffusion model for high resolution, state-of-the-art text-to-video and image-to-video generation. I'm okay with that state-of-the-art claim because to me it looks pretty much the best. Recently, latent diffusion models trained for 2D image synthesis have turned into generative video models by inserting temporal layers and fine-tuning them on small, high-quality video datasets. However, training methods vary widely, and the field has yet to agree on a unified strategy for curating the video data. So this is something that they mentioned time and time again in this paper, but I think it's important, is that data curation and like dataset preparation and dataset filtering are actually huge parts of like training these models, and people don't really talk about it too much. So in this paper, they kind of deep dive on all the different tricks that they did for that, and I think I really appreciate that. We identify and evaluate 3 different stages: text-to-image pre-training, video pre-training, and high-quality video fine-tuning. Here they're referring to the fact that if you're going to train a video diffusion model, you pretty much always start from a pre-trained image diffusion model, right? So they're starting from something like, in this case, Stable Diffusion XL or 2.1, I think they said. So that's the first pre-training step. Then you do the video pre-training, and then you do additional video fine-tuning on higher quality videos. And they're going to kind of distinguish between what a high quality and low quality video here is. We demonstrate the necessity of a well-curated pre-training dataset for generating high-quality videos and present a systematic curation process to train a strong base model, including captioning and filtering strategies. We explore the impact of fine-tuning and train a text-to-video model that is competitive with closed-source video generation. Not just competitive, I think it's state-of-the-art, and it's great. I'm very happy that state-of-the-art video generation is coming from an open source rather than one of the closed source providers like Pika or Gen 2. Gen 2 is what Runway ML has, and then Pika, I think it comes from the company called Pika. Powerful motion representation for downstream tasks, ability for camera motion specific LoRa modules. So LoRa's that produce a specific type of camera motion. Finally, we demonstrate that our model provides a strong multi-view 3D prior and can serve as a base to fine-tune a multi-view diffusion model. And this is kind of like a secret little gem here in this paper. And just last week, we were looking at a bunch of papers that are doing 3D object creation, right? So basically creating a 3D mesh or a 3D splat or something like that from text or from a single image. And pretty much all of those generative 3D models are using a two-dimensional text-to-image model as the kind of base or the prior, right? And one of the problems that people run into when trying to do generative 3D models is that the 2D image models that they're using as priors are not very good at multi-view stuff, right? They can give you the front look of a panda, but they can't give you the back of a panda's head very well, right? So they have this kind of like bias to the front. And in this paper, they go to show that actually once you take a pre-trained 2D image diffusion model and then take the extra steps needed to pre-train it on videos and then fine-tune it on videos and then create a fine-tuned video diffusion model, that video diffusion model actually has a much stronger multi-view 3D prior than the 2D image diffusion models that pretty much everybody in the 3D generative AI space is using. So that's telling you that all the papers that we read last week, where they were basically just using Stable Diffusion, not even the XL, like Stable Diffusion 1.5, to generate data to train these generative 3D models, all of those will do better once they use these video diffusion models as priors, right? And that's kind of some of the stuff that they show here, right? Is that because so many videos involve this kind of a thing where you're kind of like panning around an object, right? There's actually a lot more multi-view data in 2D video data than there is in 2D image data. So here they have, for example, panning around this kind of like little Ninja Turtle thing works a lot better with SVD, the stable video diffusion, than it does with, for example, SD 2.1 multiview. So SD 2.1 multiview is a 2D image diffusion model specifically fine-tuned for multiview with probably the end purpose being some kind of generative 3D work, right? So kind of a cool free lunch that we just got there where these video diffusion models are going to be much better priors for generative 3D work. Okay. Primarily focused on the exact arrangement. Okay, research around improvements in video modeling has primarily focused around the exact arrangement of the spatial and temporal layers. None of the aforementioned works investigate the influence of data selection. This is exactly what we just realized, right? Like, we went through all these papers, and pretty much all these papers, like, really, they're not telling you much about the data set or like how they're training or any of that. Really what they're kind of showcasing is their own little special combination of like, oh, you feed it into this encoder and then you combine it with this other encoded thing, and then you feed it into this particular control net module, which is only applied to this particular subset of the UNet diffusion model, right? So it's like pretty much all these papers are just some variant of like where exactly are you applying the conditioning, what are you conditioning with, what does your little adapter look like, are you concatenating the things, are you just using skip connect, like, right? They're all dealing with kind of like these little architecture intricacies and nuances of the pipelines. But I love this paper because they basically just shit all over that, and they're like, that's a bunch of garbage. Like, we're all just sitting here nitpicking on the exact arrangement of these layers and the adapters and like blah, blah, blah. And then it's like none of them work on the actual data selection with this is the significant impact, right? It's like that's really the only thing that fucking matters. So why don't we just actually talk about that, which is really the most important part? So in contrast to previous works, we draw on simple latent video diffusion baselines for which we fix the architecture and training scheme and assess the effect of data curation. So that's why out of all the papers that we just read this morning, I think this one, if you're only going to read one after this stream, read this one, because this one is, I think, the one that matters, because they go into the data curation process, which is actually the most important part of any of this pipeline, right? It doesn't really matter how you do your little LoRa's. Like that type of shit is kind of irrelevant, right? Like it's kind of what we were saying before, where over time, like all these little details just kind of fade away, and ultimately it's going to come down to who curated their data set the best and who has the biggest data set. So, okay, let's keep going. Little background on this. Okay, here we go. Data curation. Pre-training discussions on such data curation have been largely missing in the video generation literature, right? Not only, and part of the reason they've been missing is because it's the secret sauce, right? So the secret sauce that OpenAI has, a lot of it is this data curation, right? Dataset curation, synthetic label generation, right? So we've seen this, how, for example, in video language models, a huge performance boost comes from taking the captions that are in these captioned image data sets and then expanding and improving those captions, right? So rather than training on a data set where it's just like a picture of a dog and then it just says a dog, right? Like you improve the caption, like a particular dog sitting on a blah, 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 and like you just give more detail, and then the whole final model is better. So the more you can kind of curate and improve the data set, the more juice you're going to get from it. And that ends up being one of the most important parts. So one of the first things that they talk about here is in dataset curation, and which is basically like going through and like seeing and actually cleaning the dataset. One thing that they notice is that a lot of the videos that people train on have cuts, right? So here they have a good example here, but this here? No, this here. Yeah. So here's a source video. So here's a video that starts here and then it ends here, right? So in this video, it cuts. So it cuts from this view of the desert, and then suddenly it cuts to this view of the of a waterfall, right? So if you didn't go through your data set and you were inadvertently training on this kind of video, it would completely mess up all your shit, right? Because all of these models rely on these kind of complicated temporal attention schemes where they're really trying to pay attention to that very first frame, right? So now imagine if you were sitting there and you're training on videos where the last half of the video is completely different from the first half of the video, right? So that's going to completely mangle your video model, right? Because your video model is going to be like, wait, this should look like this, and then it's going to try to push in that direction, and it's going to mess with it. So in order to do that, and a more nefarious version of this is whenever you fade. So fade transitions, whenever you transition from like this picture of this thing and it suddenly fades. Maybe this video comes from like an architectural digest website or something like that, but it's like a picture of one room and then it fades into a picture of a different room. So they train a specific model just like a generic classification model that goes through all the videos in the data set and finds the videos where you have these cuts and these fades, right? And they filter all of those out. So here they're saying, hey, look at this. The number of clips per video, we filter out all the videos that have these weird subtle fades or subtle cuts, and look at how much crap we got rid of, right? So damn. After applying our cut detection pipeline, we obtain a significantly higher number, around 4x of clips, indicating that many video clips in the unprocessed dataset contain cuts beyond those obtained from metadata. Right? So that's huge, right? Like, think about all these people here, all these guys here, like they might not even realize that. They're sitting here thinking that, oh, the reason our model isn't working well is because we're not conditioning properly on the normalized encoded signal. Like, no, the reason it's not working is because half of your videos, or not even half, like 25% of the videos you're training on, the scene suddenly clips into something else, and now all this stuff that you're doing where you're trying to constrain it to basically look visually and appearance consistency is basically messing it up. So that's why I think this paper is so great, is because it gives you those very simple things that end up mattering a lot more. Okay. Another trick that they do is this basically synthetic captioning, which we've seen before in a couple other papers. But basically, first, we use the image captioner, COCA, to annotate the mid-frame of each clip, and then use the vblip to obtain a video-based caption, and then finally we generate a third description via an LLM-based summarization of the first two captions. So they're going to go through their whole data set, and they're basically going to add way better captions. So you can see... I think here they give you some examples. Yeah. So if you were to just naively use a single caption, right, such as here, there is a piece of wood on the floor next to tape measurement, right? Well, why don't you use more? Why don't you kind of think like an ensemble kind of approach and say, okay, well, let's caption with a bunch of different captioning models. So we're going to use COCA, which is a captioning model, where you're going to use vblip, which is video blip. Blip is an image captioning. Vblip is a video captioning. And the vblip will give you a person using a ruler to measure a wood. And then we're going to use a language model to basically consume all the different captions that we generated by sampling random frames and by using different captioning models, and then make a better, more full caption that captures the entire video. So this is kind of like a type of, they call it synthetic captioning. You could think of it like you're improving the quality of the text caption that corresponds to the video. Okay. And another type of filtering, so sorry I kind of skipped over this one, but another type of filtering that they do is for static videos, right? So they go through their entire video data set and they say, okay, if there's videos where the optical flow is like a measure of how much things in the video change. So regions of the image will move over the course of a video. High optical flow means the video is kind of moving a lot. It's changing. Things are moving. Things are changing. Low optical flow score basically means it's just like a static video. So static scenes have a negative impact on generative pre-training, so we filter them out. So they're filtering out anything that has these cuts or the fades. They're also filtering out anything that is too static, doesn't meet a specific threshold. And then they're also relabeling or recaptioning all the videos using a variety or an ensemble of captioning models, and then using a language model to basically generate even better captions based on those. So very good, tangible tips here on how to improve your data sets. And if you guys have any interest in training LoRa's, for example, I'm sure if you're watching this video, you might be interested in taking one of these stable video diffusion models and fine-tuning your own LoRa. Maybe you want to make a Pixar video diffusion model. Maybe you want to make an anime video diffusion model. And the first step to doing that is you need to curate a Pixar data set to fine-tune your little LoRa that you're going to then put on your stable video diffusion. So when you're curating that Pixar data set, you should use these tricks. Go through that curated little data set that you're going to have to make in order to train your little LoRa, and make sure there's no fades, make sure there's no clips, make sure there's no static things, augment the description of those, and so on. So I love these weed out the clips containing large amount of text. Another one. So if you definitely don't want, for example, if you just naively take every Pixar movie and cut it into clips and then train on that, there's going to be a bunch of scenes where it's basically just the title page or something like that, right? At the very beginning, at the very end of the movie, where it's just like scrolling and it's just a bunch of text. You don't want to fine tune on that, right? That's a terrible video clip to use. So get rid of those video clips. Get rid of the clips containing large amounts of written text. Okay. Systematically remove the bottom examples. Okay. Here they're talking about pre-training. I'm kind of trying to speed up a little bit here. Curated video data set. Okay, so here they show the difference here. So user preference, summarize finding. Pre-training on curated data sets consistently boosts performance of generative video models. And that's not just for video, right? This is the secret sauce for text. It's the secret sauce for images. The secret sauce for any kind of generative AI is basically you need to be very careful about curating that data set. Pre-training at small and larger scales. This performance persists even after 50K steps of video fine-tuning. Okay, uncurated, curated. So here the orange is uncurated, and then curated is the blue. So you can see the blue bar is always higher than these orange bars. So it just goes to show you the performance boost you get from curating. And the way that they're measuring the performance here is with user preference, which I actually think is the best one, right? Sometimes in these generative papers, they use something like a Fréchet inception distance or these other types of quantitative metrics, but I think those are kind of garbage because they don't really tell you. It's hard to actually know if they're correct or not. So the way that they do it is what I think is the gold standard, which is these basically user studies where someone basically sits and they just, I don't know how they do this. I guess they probably use Mechanical Turk, and then you have like kind of like random people all over the decentralized internet get paid like 4 cents per image to basically sit there and say, I like this one, I like this one, I like this one. So this is what they're seeing. They're seeing they get shown 2 images or 2 video clips here, and they say, which video looks more realistic and higher quality? And then you click on this one. Which video looks more representative to the text? So it says a lion standing on a surfboard, and you're like, okay, well, this one looks better, and I click on that, right? And you can kind of think of this like a game, right? So this video is competing with this video. So in a sense, ultimately what you're going to get out of this is a score, and you're going to get what's called an ELO score. So ELO score is a scoring system. It's a rating system that was, I think, originally designed for chess, where basically it's a way of saying who's good at chess and who's bad at chess, and then every individual game that you play, you can increase your ELO score or decrease your ELO score, but the amount that it increases and decreases is based on the rating of your rating and the other rating. So if Magnus Carlsen beats like someone who has a terrible rating, it's not going to change his rating very much at all. But if someone who's very trash beats Magnus Carlsen, their rating is going to suddenly go up much higher, right? So it's kind of like a rating system for competitions that is like takes into account the relative rating between those. So they eventually by using this, they're effectively creating and competing these different versions of the video diffusion, and they can say, okay, well, the ELO of the uncurated data, or the ELO of the video generation model trained on the uncurated data set versus the ELO of the curated, or the ELO of the video generation model trained on the curated data. So that's what they're basically the y-axis here is. Okay. Finally, we show that dataset size is also a crucial factor when training on curated dataset. A model trained on 50 million curated samples is superior to a model trained on LVD 10MF for the same number of steps. So I thought this was important to highlight because sometimes people kind of drink the data curation Kool-Aid too much, and they're like, oh, it's all about data curation. It really doesn't matter. We don't need to train on huge-ass data sets. We just need to train on very small curated data sets. And no, that's not the answer either, right? It's like, the big ass data set matters, but you also need to curate it. It's like both, like you need both of them. You need more data is better, but then curated data is better than non-curated data. Okay. I think, was there other things here? So this kind of shows you the quality here. I feel like the quality for this is unparalleled, way better than some of the other qualities that we were looking. And here's their little state of the art. So Gen 2 and Pika Labs are the closed source models, right? And they used them in the same kind of little ELO thing, and they had people pick, and look at that. Stable Video Diffusion is better than Pika. Stable Video Diffusion is better than Gen 2. So rather than going and purchasing a subscription to Pika or purchasing a subscription to Runway ML and their closed source solutions, why don't you just come over here into Hugging Face or into Replicate or any kind of open source model hub and use this one, because it's free and they told us how they did it and they're being open source about it. So, support your fellow open source AI contributors and use open source products instead of these fucking closed source products. Fuck them, Okay. They start from Stable Diffusion 2.1. That's going to be their pre-trained image diffusion model that they start from. Blah blah blah. Fine-tune the model on. I think they're doing the high quality, low quality. They use a smaller, shittier videos, and then they go to higher quality videos. Is there other things here? This paper has a really good appendix section, like super top tier appendix section here. Yeah, this was the point that I wanted to talk about before, where multi-view generation is very important, not because anybody actually gives a shit about multi-view generation, but because multi-view generation is used for generative 3D models, right? Generative 3D models are, almost all of them are in some way using a multi-view 2D diffusion model as a prior, right? So which is what this paper is saying, if they would have used a video diffusion model, the video diffusion model is a much better candidate for the multi-view generation, as multi-view images form a specific type of video where the camera is moving around an object. Basically, it's saying that video data sets, you always end up in this situation where you're basically like painting around an object, and that is effectively multi-view data. So these video models are much better multi-view models. What do we got here? Concise summary of diffusion models. There's a little summary of diffusion models. Classifier-free guidance. I think they also had a little trick here for the classifier. Yeah, they do linearly increasing guidance technique. So guidance is basically a measure of how much the control signal in your UNet diffusion model is, how much strength it has, right? So whenever you're removing or denoising from a latent space, you're conditioning usually on text, right? And the strength of that text conditioning, but it can be something else, is basically this guidance, what they call the guidance here, right? Where is it? Guidance, classifier-free guidance, is a method used to guide the iterative refinement process towards a conditioning signal C, which might be text, right? So I don't know if I've seen this before, but in this paper, they basically schedule this, right? So most people know about learning rate scheduling, right? Where you're changing the learning rate over the course of a training process because you probably want a higher learning rate initially and then a lower learning rate, or maybe you want to do some kind of like kind of up and down, kind of like a cosine sine type schedule where it increases learning rate, then decreases learning rate, then increases learning rate, then decreases learning rate. But this type of scheduling is not just for learning rate, right? People also use schedules for the noise. So the amount of noise in your diffusion model changes over where exactly you are in the diffusion process, right? So earlier on in the diffusion process, when you have a lot of noise, you can remove a lot of noise, versus later on in the diffusion process, when you're really just trying to really get the last finishing touches on that image, you probably don't want as much noise. So we know that learning rate scheduling is a thing. We know that noise scheduling is a thing. And now in this paper, they say, okay, well, actually, you can also schedule the guidance, classifier-free guidance parameter, right? So that's, I'm sure some other paper has done it. Like this is probably like a Schmidt-Huber type situation where like someone can dig up some like random old paper where someone scheduled the classifier-free guidance, but they do that in this paper. They call it novel, so I'm sure they probably did a little bit of research to make sure that they were the first people to do that, but that's something cool. What else we got? They used A100 GPUs with 80 gigabytes of VRAM. So if you were curious about that. And then 55. Okay, we're basically there. I don't know. I really like this paper. I think it's the highest quality, and it's also it's not just the highest quality in terms of like the actual final result, but it's also the highest quality paper. Like this paper just tells you literally everything. They focus on the data. They focus on the things that matter. They give you actionable, tangible suggestions on how to improve your dataset quality. And I think they use the best metric, right, with this user study. So very good metric, very good results, very good paper. You love to see it. All right. I'm going to sip this coffee, drink some water. If you guys have any question, put it on there, and then we'll summarize and then go from there. All right. Guys, been blasting off here. Have you seen Gaussian Editor? I have seen it. Someone posted it on the Discord. Tomorrow we're going to be doing streams on the Gaussian codec avatars, so maybe we can talk about the Gaussian editor there as well. The Gaussian splats they're moving really fast. You know, they're getting really popular really quickly. So more and more, it seems like we're doing streams on Gaussian splats. Photogrammetry. Captioning. Schmidhuber, slicing your bread is all you need. So far, all the AI art with movement does it only slightly. 5 pictures that break over time. Is this a step change of sorts? I would say, like, I think this is usable. Like, you can definitely use this. And I've already started to see YouTube videos and, like, content creators that are using these video diffusion models and kind of just weaving them in. I agree that it's not quite at the quality yet where you're going to see this in like a Hollywood movie. You're probably not going to see like 2-hour movies that are entirely done with video diffusion for at least a couple years, but we're making progress quickly. So yeah, I think to me, this stable video diffusion is the state of the art. Here's the figure to prove it. I think it beats Pika and Gen 2. And I also think you want to support this team, dude. This team is awesome. You know, they're super open source. I love the way that they do things, and I love their papers. Okay. So why don't we just maybe summarize about the stream, and then we'll go from there. So in today's stream, we're looking at video diffusion models, and we reviewed a bunch of different video diffusion models and similar-ish models that have come out in the past couple weeks. We started off with basically some control net type models, if you want to think of it that way. So we started off with this one, Magic Animate from ByteDance, which is the TikTok company, and they basically create a pipeline that allows you to take a reference image, such as this 2D image here, and then condition it on a sequence of poses, in this case, dense pose, which actually I think comes from Facebook as the dense pose paper originally, and then it'll basically modify that image and create a video from it. Let's see. Yeah, there wasn't really anything that fancy here, but what else? We also looked at this paper, very similar again, also another Chinese AI group, this time Alibaba, and also very similar in that they're trying to showcase their results with waifus and kind of like weird sexualized videos, but same kind of idea, right? You're basically conditioning a video diffusion model with poses, in this case a slightly different type of pose, and going from a reference image. What else? That's that. Then we had this one. So this was work from Adobe. And this is basically, I think, the best out of all these conditioned models, but you need to basically condition it on a slightly better type of signal. So the other two previous papers, they condition on pose skeletons and then dense pose. But this one here, they're conditioning on a UV map and a depth image. So these are much stronger control signals, which allows you to do kind of these little tricks where they basically rather than using random noise for each frame of the video, they basically are being clever and using the same noise wrapped onto the actual parts of the image that are relevant. They do the same kind of wrapping with the actual features, right? So they're kind of using the fact that the UV map gives you these hard separation boundaries between what is background, what is foreground, what is the head of the fox, the foot of the fox, and so on. And they use that to basically more effectively control the diffusion for this video generation. So you can see the quality is a little bit better than these other papers, but it's also because they're starting from kind of a stronger control signal. Then we looked at this one. So this is another paper by a Chinese AI research group. This one's coming from Tencent, which is the company that does WeChat. I think they also do League of Legends, believe it or not, like kind of a weird combo there. But in this one, you can basically condition your video generation on a trajectory of camera motions and a object trajectory. So camera poses are going to be basically these 12 numbers that represent the position of camera in 3D space, the position and rotation. You have a trajectory of those, sequence of those, and then you can basically condition the video generation on that. Same thing with these object poses. What else? We got, that's the actual motion control paper. This is the video diffusion model that they start from, which is the Tencent video diffusion model. Then we had this one, which is another Tencent paper. This one is more, it doesn't have a control signal, so they're not controlling the video generation with some kind of external pose or some kind of camera motion or anything like that. Really, it's just coming from this first image. So all the subsequent images in this video are basically being kind of like forced to look like that first frame. The way they do that is basically by duplicating the keys of the first frame. Kind of a little trick, kind of similar to KV caching there. But I feel like this type of stuff is like, what's the use of this, right? Just kind of like give a little bit of motion into an image. Like, I don't know, maybe for like profile pictures or something. Then we looked at Dream Video, which is another Alibaba paper here. And in this one, they basically train two separate LoRa's. They train a little LoRa for the subject, such as this dog, and then they train a little LoRa for the motion for a specific video. And then those two LoRa's, they basically then combine them, and then you can now create a video that kind of combines the subject, such as a dog, with the motion of this video. So you get the dog playing guitar and so on. I thought that it was kind of cool how they basically use what looks like a LoRa, but it's slightly different because it has this nonlinear layer in between. So I thought this was kind of cool. I wonder if you could do this for other LoRa papers, whether that would even work or not. Okay, and then the final thing we looked at was the paper associated with the stable video diffusion, which again I think is the state of the art in terms of video diffusion models. And this paper talks a lot about dataset curation, and they basically show that one of the most important things you could do in creating a high-quality video from the subjective evaluation of human evaluators is to basically curate your data set. And they kind of show you some examples here of basically getting rid of fades in your video data set, getting rid of hard clips in your or cuts in your video data set, getting rid of stationary videos, and improving the captions of these videos with an ensemble of captioning models, and then using LLMs to even further add juice to that. So that's pretty much it, guys. Video diffusion, it's looking good. You know, I can't wait to see what this looks like a year from now. I think a year from now, this is going to be next level. You know, I think we're looking at the early versions of it, and yeah, they're only a couple second long. They're only like these little short clips, but you know, give it another year, and I think we're pretty much going to be watching AI-generated content. I don't know. I think that's it, guys. Thank you, Spirobell. Thank you, Julian. Thank you, Josh, Daniel, Ruslan. Who else? Liu, Payne, Ice, Huge, Minotaur, and Ed. Thanks, everybody. Thanks for watching. Hope you guys found this useful. And if you're interested in Gaussian splats, check out tomorrow's stream. That's what we're going to be going over tomorrow. If not, see you later. Have a great weekend.